All right, welcome to Friday. Hopefully you're getting back into the swing of things. Let's create some homework. Go ahead and get out 11.3. All right, there's a lot to call out here. So here we go. Number one, I think all of these have, what, 2 answers? Any of them have 3? No, it looks like all of them have 2 answers. Okay, so here we go. Number one, the area is 70 and the median is 10. Number 2, the area is 30.5 and the median is 5. Number 3, the area is 6. The median is 3.75 or 3 3/4. Number 4, the height is 10 and the median is 30. Number 5, the height is 5 and the median is 18. Number 6, the second base is 5 and the median is 4. Number 7, the second base is 1 and the median is 4. And number 8, the first base is 15K and the median is 9K. 9K. All right. Number 9, the median is 9. Number 10, the area is 64. Number 11, the area is 108. Number 12, the area is 21 root 3. These are the ones involving special right triangles. Number 13, the area is 27 root 3 over 4. 27 root 3 over 4. Number 14, the area is 94.5. 94.5. Number 15, the area is 24. 24. Number 16, the area is 180. Number 17, the area is 128. Number 18, the area is 65. 65. All right, these last 3 involve some trig, so they weren't special right triangles. 19, the area is 42, and I'm rounding to the nearest tenth here. 20, the area is 71. And the last one, 21, the area is 87.8. 87.8. One word of caution, we got to make sure we're doing our homework. If there's a number of these you're getting wrong, well, you just heard the answers, I strongly encourage you to go back and redo the problems. And if you're still having an issues, hey, we got plenty of time. Email me. Let me help you understand a specific problem or two. Since I'm not there to crack the whip, I know it's really easy to get lazy. And I guys need you to be virtuous and do the right thing and make sure you're getting this stuff done. Okay, enough of a speech. Yeah, it's Friday, so same drill next week, and then the week after that, we'll have a test on that Friday. So the test will work as normal, except it'll be an online test. It will be a multiple choice test. Yay! Obviously, there's no way that I can specifically time you. I do have the option of opening up the test at a certain time and closing it at a certain time. I'm just worried about technology issues. If the computer crashes or there's bandwidth issues or something like that, Wi-Fi goes out. I'm not going to do that. I'm going to give you, I'll probably give you, a normal time at your leisure to take the test. But when I mean at your leisure, I mean not 2 days to take the test or over the weekend to take the test. But I'll give you you can take the test at any point you want, and it'll be a normal 50-minute test. And I just ask you guys to be responsible and virtuous and make sure you only use 50 minutes. But it's still the same rules. It's open note using the book of knowledge. Calculators are permitted. Type thing, and you're going to need them because some of them are going to be trig problems. So you know the drill. Just trying to ask you guys to be good students. All right, here's your homework for tonight, or I should say tonight and the following, since we're doing day on, day off type thing. So I haven't actually given you more homework. I know some teachers since you have 2 days to get this completed, they're cranking up the homework a little bit. I'm keeping the homework the same. I'm just asking you to, now you absolutely have time to devote to every one of these problems, and there shouldn't be any problem that you have unanswered, meaning like, typically on a normal class period, I couldn't get number 17 done, I'll come back the next day and I'll ask questions. Well, now you have the time to ask those questions, so send me an email. So you should get all your homework done. So if you have any issues on any one of these specific ones, hey, make sure you email me, and that way you'll get them all done. Okay, I like this one. This is a fun one. This is, there's a few formulas in geometry that are really I don't know, magical, special. I don't know, those are not really good words, but just really are really interesting formulas. The more interesting formulas are the simple formulas. The formulas that take a whole whiteboard to write. I don't find those very interesting. I don't think they're elegant. This one is a really elegant formula. All right, so it's just one theorem. It seems like we're following a pattern. We're only getting one theorem a day type thing. Okay, so here we go. Think about this. We've talked about polygons. These are closed plane figures constructed of segments joined at their endpoints. We've studied many of them, a triangle being one of them. A triangle is made up of 3 segments, and those segments are joined at their endpoints. Okay. Today we're going to be talking about a special type of polygon, and that's not how many sides, but a special type. And we've talked about this before. You've written this definition down before. We're going to be talking about regular polygons. And if you recall, regular polygons are polygons whose sides are all the same measurement and whose angles are all the same measurement. This is the definition that's written in the book. I don't like it because it gives you the impression that the sides and the angles are exactly the same number. That's not what it means. It just means a shape, such as an equilateral triangle. Equilateral triangle is regular. That means all the angles are the same measurements, right? 60, 60, 60. And all the sides are the same measurement, 10, 10, 10. Okay? It doesn't mean that the side measurement equals the angle measurement. Okay. So today we're only going to be dealing with regular polygons. Regular polygons. Okay, so here we go. It turns out if you have a regular polygon, so once again, we're only dealing with regular polygons today. If you have a regular polygon, that you can inscribe regular polygons inside of circles. For instance, the equilateral triangle is inscribed inside that circle, or the circle circumscribes that triangle. A square can be inscribed. A regular pentagon can be inscribed, so forth and so on. Notice they all fit nice and neatly inside a circle. Okay. This is not the case with an irregular pentagon. Notice if I put an irregular pentagon, I'll never be able to actually touch all the vertices. Now there are two exceptions to this. All rectangles can be inscribed, and also any triangle can be inscribed. But that's the 2 exceptions. But all regular polygons can be inscribed in a circle, or they can be circumscribed. All right, so here comes some weird definitions. You're going to need to write these down, pause the video, that sort of thing. Definitions are going to be important because we're going to use this terminology. All right, so the first one is called the center of a regular polygon. Center of a regular polygon. And the basic definition is the center of a regular polygon is the center of the circumscribed circle about that polygon. So notice there's a pentagon inscribed inside that circle, or there's a circle that circumscribes that pentagon. So the center of the pentagon is exactly the same as the center of the circle. Okay? So there's your first definition. You may want to play that a couple times to wrap your head around what's going on there. All right, the second definition is called the radius of a regular polygon. We will define the radius of a regular polygon as the distance from the center to its vertex. And it should say to any vertex. Well, this would also be the radius of the circumscribed circle. Notice, if I draw a line, or line segment from the center of the polygon to any one of its vertices, that would also be the radius of the circle. And that should make common sense. Okay, so go ahead and pause the video, make sure you have this written down. And if you need to draw the picture, draw the picture. Okay, so the definitions don't stop here. We got a couple more. All right, so here comes the next one. It's called the central angle of a regular polygon, the central angle. We've talked about the central angle of the circle. That's the angle that comes from the center of the circle, and it's exactly the same for the polygon. So if you take a regular polygon and you inscribe it in a circle, or you circumscribe the circle around the polygon itself, and then you draw one radius, right? So remember, we define this radius that goes from the center to a vertice, and you draw a consecutive, or a radius to a consecutive vertice. Notice I can't go to an opposite. I got to go to a consecutive one. I actually make a central angle, and in red there, hopefully you can see the central angle. Okay, so the central angle of a regular polygon is the angle formed by two radii drawn to two consecutive vertices. Okay, hopefully that makes sense. Okay, final definition of the day is called, brand new word, it's called the apothum. Apothum. And the apothum is, well, it's the other obvious distance that's listed right there. It would be the distance from the center of the polygon to the side of the polygon. So notice in blue there, and it would be measured perpendicularly, right? So it's called the perpendicular distance to the side of a polygon. So that's measured from the center of the polygon to any one of its sides. And this distance would not change. It would be the same no matter what. Okay? All right. So those are the 4 definitions that we have for today, and we will be using those words. All right. So we're going to do kind of proof. This is called an informal proof. Sometimes it's called a talking proof. And we basically, we take the idea of a proof. It's still rigorous, right? We just basically talk about it, right? It's very close to a paragraph proof. The difference is it's just not written in paragraph form. So all I'm going to do is just talk you through the proof itself. It's still a rigorous proof. We just call it informal because we don't follow, I don't know, a set standard. We don't put things in a specific place. We just simply talk about it. All right, so here we go. I'm going to prove something to you. Think about this. If I take any regular polygon, I'm going to take an octagon. And remember, a regular polygon means that all the sides are the same. Okay, so that's actually Theorem 11.6, and we just proved it. And it says basically if you have a regular polygon, then you want to calculate the area, it's 1/2 times the perimeter times the apothum. P for perimeter, A for apothum. Make sense? Hey, we just proved that too. That was an informal proof. And for most people, I think most people do like informal proofs. Okay. Quick note of caution. Hey, this only works for regular polygons, and also you have to use the apothum, not the radius of the polygon. The radius of the polygon, I've shown it right here, is what's listed right there as R, but we need the apothum. We need the perimeter, and we need the apothum. We do not need the radius. However, because this is geometry and they love to make it more challenging than it necessarily has to be, sometimes they're going to give us the radius, and we'll have to calculate the apothum. So just remember, we're going to be calculating distances of a right triangle. So we have basically, 3 tools in our books. We have the Pythagorean theorem, we have special right triangles, and we have trig, okay, or any combination thereof. All right. All right, just so you know, before you took the geometry class, you already calculated areas of triangles, you already calculated areas of quadrilaterals, but you never calculated the area of any shape larger than a quadrilateral. And the reason for that is, well, you got to have some geometry knowledge. And that's also why they don't have that in any book before geometry. So today we're going to be calculating, and going from here, you're going to have the ability to calculate the areas of regular polygons. All right, so these are going to be 2 big boy, big girl problems. These are going to involve a lot of stuff. So these aren't going to be your simple, hey, just plug 2 numbers into a formula and do the calculation. All right, so we're going to do 2 examples. I strongly encourage you to work along with me. All right, so here we go. So let's see, what do I got? I got a regular hexagon, and it looks like I got an apothum of 9. An apothum of 9. That's all I got. I don't have anything else. Notice I don't have any side distances. I don't have a radius. All I have is an apothum. Well, it turns out that we can calculate the area of this hexagon simply by knowing its apothum. All right? Well, we know the basic formula is 1/2 PA, and I know that A now is 9, so I just need to calculate the perimeter, and I'm done. So the question is, how do we calculate the perimeter? And I kind of already given it away, and I said that with the apothum, and the radius that you always get right triangles. So we have lots of tools in our toolbook. We have trig, we have Pythagorean theorem, and we have special right triangles. So let's see if we can calculate the side distance. Well, notice, I can't use Pythagorean theorem because I only have one distance. I can't use special right triangles, or can I use special right triangles? Let's see. Or trig, because I need degrees. So let's see if we can somehow tease out degree measurements from that triangle right there. So I drew the two radii. Do you see what I did there in red? I drew the two radii. We know it's a hexagon. Can we say something about these angle measurements? Can we say anything about the angle measurements? So look at the top vertex there, at the point at the center. Can we say anything about those angles, right? There's two angles right there, right? Or one if you want to combine them. Well, we know it's a hexagon. So how many degrees in a circle? 360. So how many of those red triangles would you actually form if you put them all on that hexagon? You'd form 6 of them. And since it's regular, that means each triangle is the same measurement. Well, 6 goes into 360, 60 times. So that means that entire angle there is 60, and that, I don't know, if you cut it in half, then therefore that is 30. That's kind of the trick that you're going to use tonight for homework for many of the ones. When you're dealing with a regular polygon, you're going to know that the central angle right there, well, 360 degrees in a circle. You know it's a hexagon, so that means there'd be 6 of those triangles. The larger triangles, ignore the apothem for a second. Therefore, 6 goes into 360 60 times. So the central angle, ignoring the apothem there for a second, would be 60 degrees. Therefore, one of those angles would be 30 degrees. That makes sense? And we've already shown that that would be an isosceles triangle, right? Because the radii would be equal. Okay, so hopefully that logic made sense and where I got the 30 from. All right, so once we have that one angle, now we have 2 options. We can either use trig, or we can use, in this case, since it's 30 degrees, we can use special right triangles, because we know then, therefore, if that one's 60 and the other one's 90. So for me, whenever there's a special right triangle, it's a little bit easier than trigs because I don't need a calculator. I can do this by hand. Of course, you do need to remember your special right triangles. So there's our triangle right there. We're trying to find out what x is, right? And we know what the long leg is. The long leg is root 3 times x. And we know that that is equal to 9. Does that make sense? You following along? So we know that that was 9. That was our only given thing, which was the apothem was 9. So we simply solve for x now. So let's see. We divide both sides by root 3. Then when we rationalize it, top and bottom times root 3. So therefore, we would get 9 root 3 over 3, which reduces to 3 root 3. Okay, so we know that the x value now, x value is 3 root 3, and since both of those triangles are congruent to each other, that means the other side is also 3 root 3. So that means that s, that entire length of that triangle, the red one there, will be what, 6 root 3? But one side is 6, therefore P is the perimeter. There's 6 sides. So let's see, 6 times 6 root 3 would be 36 root 3. Do you see where I got the P from? Right, there's 6 sides. One side is 6 root 3, therefore 36 root 3. All right, if you need to rewind the video, please do. Follow that logic. All right, so now it's just a matter of doing a little bit of cleanup right here. There's multiple ways you can do this. I don't know, half of 36 is 18. 18 times 9 is 18 times 9 is 162. 162. So 162 root 3 square units. Wow, that was a lot of work. That was a lot of work. A lot of work. All right, we're going to do one more. Okay, so the previous one, all we were given was the apothem, and now all we're given is a radius. And it says example up there. The instructions should say, find the area of the regular, what is this? How many sides we got here? 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there's 9 sides. 9 sides. So this is a 9-sided regular polygon. We're going to calculate the area simply from the radius. Well, notice our formula doesn't have anything to do with the radius. I need the perimeter and I need the apothem. All right, we're going to do the same drill as the previous one. And I'll just say for homework, it's going to be the same drill each and every time. Okay, you're going to make the triangle, right? And remember, since it's regular, that means there's 9 of these in that entire polygon. The apothem is that distance right there, and I need that distance. So that's going to be the first thing. So we got three tools. We got Pythagorean theorem, we got special right triangles, and we have trig. So first step will be to find that central angle. Ignore the apothem there for a second. So let's see. There's 9 sides, so there's 9 triangles. There's 360 degrees in a circle. So 360 divided by 9 is 40, so that means the central angle is 40, so that means that one of those angles is 20. Okay, does that make sense? Once again, central angle will be 40 because there's 9 sides. 360 divided by 9 is 40. Therefore, one of those angles there is 20. All right, so we can't use special right triangle. I still can't use Pythagorean theorem. Eventually, there might be a case where I could use Pythagorean theorem. I'd have to have 2 sides of the triangle. Okay, so we got to use trig this time. So let's see. What am I trying to find here? I'm trying to find I'm trying to find the apothem, right? The apothem. I also need to find the perimeter, so that would be the opposite side. The apothem would be the adjacent side, and the opposite side, I would need that for perimeter. It doesn't matter which one you solve first. I'm going to find the perimeter first. So I'm first going to find the opposite side. So let's see, which trig function uses opposite? Well, tangent uses opposite, opposite and adjacent. Nope, that would be 2 unknowns. So we got the hypotenuse. The hypotenuse is 10, so we want to use sine. So sine of 20 is going to be equal to the opposite side, which would be x, all over the hypotenuse, which is 10. Does that make sense? Okay. All right, so we need to do a little bit of algebra. Multiply both sides by 10. Grab your calculators. So 10 sine 20. Just remember, make sure your calculator is in degrees, not radians. 10 sine 20. Now, we're going to have to do some rounding here, so we'll round to the nearest tenth. Is about 3.4. So I just found out that the opposite side is 3.4. If that part is 3.4, then that part is 3.4, meaning the whole side is 6.8. Now I can do the perimeter. How many sides? There's 9. 9 times 6.8, about 61.2. Okay? Makes sense? All right. Now we got to find the apothem. The apothem. Well, we could use Pythagorean theorem, 3.4 squared plus x squared is equal to 10 squared. You could do that. Since I'm already set up for trig, I'm just going to use trig again. But Pythagorean theorem would give it as well, too. So let's see. I'm trying to find the adjacent side this time. So which one has the adjacent? Both tangent and cosine. I mean, I could use tangent, opposite over adjacent. So that'd be 3.4 over the adjacent. Or I could use cosine as well, too. I'm going to use cosine. And you notice I typically like it when the variable is on the top, and that way you have to do the least amount of algebra. So that would be 10 cosine 20. Grab your calculators. We find out it's about 9.4. 9.4. All right. So that means the apothem is 9.4. We plug that into our formula. We simply do the math. 0.5 times 61.2 times 9.54, is 287.6 square units. Holy moly, that was a lot of work. Okay, we only did 2 examples. As always, right? Homework will be slightly challenging. You'll get into the swing of things. I tried to give you at least 2 examples that would give you a flavor of the things that you'll have to do. The only thing we did not do there was Pythagorean theorem. There's a few that you might need to do the Pythagorean theorem on. Remember, if you ever have 2 sides of a right triangle, find a third, use Pythagorean theorem. But also remember, there's nothing wrong with using a little bit of trig as well, too. Okay? All right, and then lastly, obviously, special right triangles. So for those of you that just need a quick reminder, there's your 2 we didn't do a 45, 45, 90. Just remember the 2 legs are x, and the hypotenuse is x root 2 or root 2 times x, whichever one you like. All right, so there's 2 examples. I fully anticipate a couple of you might email me on a question or 2, and that's fine. Don't hesitate, no matter what time, send me an email. I'll try to get back to you, within the hour for sure. If it's a Monday through Friday, I literally just hang by my my laptop the whole day. If it's Saturday and Sunday, yeah, I'll get back with you within an hour of your question type thing. So that kind of concludes the class for today. It seemed like that was kind of quick. Well, we really only did 2 examples. So you guys have a great weekend. Email me if you need any help on this, and I will see you guys on Monday.